talking about graphing polynomials. So I'm just going to start out by writing out the steps for how we're going to do this so that we can follow from there. 1, our first task is to put the polynomial in root form. Once we have the polynomial in root form, there are a bunch of things we can tell from root form. So from root form, we can find roots, of course, including x-intercepts. What kind of roots are x-intercepts? Are real roots. We can find our roots, including the x-intercepts. We can also see the multiplicities. What is the multiplicity of a root again? Well, remember, it's the number of times that a root shows up in the list of roots, right? And that will tell us, the multiplicity will tell us the shape of the graph at that root. We'll see some examples in just a second. Last but not least, we can determine the end behavior of the graph. I'm going to write more about this in just a second, so I'm going to give it a little asterisk. 3. Then we can use this information to graph. So a quick note on end behavior. So let's think about a polynomial that we have found the end behavior for in the past. The polynomials that we've looked at the most so far are quadratics. For quadratics, a, which is what in the context of a quadratic? I guess also in all polynomials. We've been using a to represent the leading coefficient. If a is greater than 0, what did that tell us about a quadratic? It told us that it opens up, right? And a being less than 0 meant that the parabola opens down. How does this extend to greater degree polynomials? Well, this generalizes to higher degree polynomials. Oop, squished it on accident. If the leading coefficient is positive, that means that a is greater than 0, then we have the following end behavior. F of x approaches positive infinity, which normally we would just write as infinity, but I want to emphasize that it's positive infinity as x goes to infinity. If a is negative, f of x approaches negative infinity as x approaches infinity. So what does this mean? So remember that when we're talking about when x goes to infinity, right, x approaches infinity on the right side of the graph, right? The x-axis is positive on the right side. So this is saying that our leading coefficient, the sign of our leading coefficient, if it's positive, it means that our y values are positive, right? We're continuing off the graph to infinity, right? If a is negative, then our y values, right, the value of the function, is getting really, really small, right? So we're moving off the graph downwards. So another way to say this is the sign of the leading coefficient tells us the direction of the right side of the graph. So if a is greater than 0, our graph has something going on. We're not sure what, but we know that it ends in this way. And if our graph, if a is negative, right, if a is less than 0, then we don't really know what's going on with the graph. We don't know where it crosses the x-axis. It could be doing whatever, but we do know that it ends like this. Okay, let's give this a shot. Let's open up the lab manual to graphing polynomials. Let's start out with this first one here. This is a quadratic. We've had plenty of practice graphing quadratics. Our first move is to put it in root form. That means to factor. So putting this in root form, what multiplies up to 4 and adds up to 4? Positive 2 and positive 2. Remember, from root form, we can determine a few things, right? End behavior. So, no. Our first is our roots. How many roots are we going to have, first of all? Well, 2, right? That's the degree of the function. The degree of this function is 2, so we have 2 roots. And both of them are negative 2. So that means we have a multiplicity of 2 at negative 2. We have this root here. We also know that our leading coefficient is 1, right? Leading coefficient is 1, which is greater than 0. So that means that our end behavior of our graph, as we move off the graph to the right, we're going to move upwards. I like to note it with a star. It kind of helps. I also know that at the point negative 2, 0, right, at that root, because it has a multiplicity of 2, because it shows up in our list of roots twice, it's going to look like a quadratic at that point. So we know we have this parabola that hits the x-axis at negative 2 and it opens upward. Let's do the same thing for number 3 here. This is already totally factored for us, so the first thing we need to do is just find our roots. So remember, our roots are the x values that will make this function equal to 0, so the x values that will make any of the factors equal to 0. The first factor with an x that we have is x. When is x 0? Sounds like a trick question, right? It's 0 when it's 0, right? X equals 0 will make this function equal to 0. So we have 0. It has an exponent of 2, so we have 2 of them. Our second root is x plus 4, which means we have the root negative 4. And how many times does it show up? Well, it has an exponent of 3, so that means we're going to have 3 negative 4s. So we have to draw 2 points on the graph, right? We have to draw 0 as an x-intercept, and we also have to draw -4 as an x-intercept. That's right here. What do we know about the end behavior of the graph? Well, let's look at our leading coefficient. 3 is, of course, greater than 0. So, because it's positive, the end behavior of the graph, as we move off the graph to the right, the graph is going to be getting large, right? The y values are going to approach positive infinity. So I'm going to put a star there to know, so that we know that we need to end up in this kind of corner. Okay, so what is the graph going to look like at 0? Well, at 0, we have a multiplicity of 2, which means it's going to look like a parabola close to that point. So we know that we're starting up here, so we can kind of come down, and as we pass through that point, right, we have a parabola shape, so we kind of bounce back up. Then when we get to -4, what's the multiplicity of -4? How many times does it show up in this list of roots? 3 times, right? So we know that we're going to need to make it look like a cubic function. So I'm going to have to curl back down. Cubic functions have that sort of wiggle, right? Just like that. And then we continue down. So our graph looks like this. It's totally okay that we're not exactly sure exactly what all the points are, right? Maybe you made this part taller, or maybe you made this kind of steeper, this part steeper or something. It's totally okay that these drawings are approximate as long as we know sort of these general shapes around the roots and the end behavior. So my list of roots here. My first factor with an x in it is x plus 2. That means I'm going to have the root -2. How many times does it show up? Well, there's only one factor, so it's only going to show up one time. X minus 4 is going to give us a root of 4, and it has an exponent of 2, which means there's actually 2 factors of x minus 4. So 4 shows up twice. All right, let's graph those x values. We've got -2 and +4. What does our leading coefficient tell us about our end behavior? Well, we've got -2, which is less than 0. It's negative, so we're actually going to move off the graph in the negative direction. So we need to be kind of pointing towards this corner here. So our graph is going to start off like that. As we move through the point 4, 0, we know that we have 2 of those roots. So the multiplicity is 2. So it's going to look like x squared. It's going to look like a parabola as we touch the x-axis there, just like that. As we continue on to the point -2, 0, we know that it has a multiplicity of 1, which means that we just pass straight through it, like a line, kind of. And that's what my function looks like. Why don't you guys try number 2 here? Write out the list of roots, make sure that it's easy to tell what their multiplicities are, check the leading coefficient for end behavior, and then graph it. Okay, so looks like we had 3 roots, one at 5, 4, and -1. We also had a leading coefficient that was negative, so our graph is sort of pointing downwards as we move off to the right. But as we move through, each of these x-intercepts have a multiplicity of 1. So as we pass through each of them, we're just passing straight through, right? So we don't have any bouncing off or weird cubic shapes. We're just passing straight through. So this is our graph. Again, if you made this taller, or the way, how deep your this dip goes or how steep this end is or whatever. That doesn't matter. We just need to make sure that we have the multiplicity shape correct and also the roots and the end behavior. That's it. Okay, let's check out the next page really quickly. So looking at this first one, what do we need to do first here? Well, remember our very first step is to write the function in root form. Is this in root form? It really looks almost like root form, but remember, root form is a times x minus r1 times x minus r2 times x minus r3 for however many roots there are, right? X minus the root, not root minus x. So we need to kind of modify this so that it's truly in root form before we continue. How can we do that? How can we make 3 minus x look like x minus something? Let's start by writing it with the x first. So that would mean we have negative x plus 3 times x minus 4 cubed. So now, in order to get the x by itself, we have to get rid of this negative, which we can do by simply factoring, right? So I divide each term by -1. The negative comes out front. That gets the x by itself. If I divide positive 3 by -1, what happens? I end up with -3, x minus 4 cubed. Oops, forgot parentheses there. So this has actually done something important, right? If we look at this and we were looking for the leading coefficient of this on its own, right, we would say, oh, it's +1, right, because there's nothing out front. But making this factor, putting this factor into the proper form, gave us a leading coefficient that was negative, and that's going to change our end behavior. So speaking of that, let's draw our asterisk down here. We know we need to aim for this kind of corner here. What are the roots that we have now? Roots of this function are, we have 1 at 3, and then we have 4 as well, but because of this exponent, we have 3 4s actually. So we've got 3 and 4. We know we're starting down here. As we approach +4, we know that the shape of the graph, because there's 3, it has a multiplicity of 3, so we're going to have a cubic shape. So we kind of have to make that cubic shape pretty small, and then we really quickly have to turn back around and pass straight through, right? 3 has a multiplicity of 1, so we pass straight through 3 and continue down. Let's do one more of these. So number 7, we have 2 times 4 minus x times x plus 1. We need to switch this factor around again, right? So let's write it so that x comes first. Negative x plus 4 times x plus 1 squared. We need to pull this negative out. So we factor out the negative. It comes out front. So we have -2, right? Or 2 times -1 or whatever, which ends up being -2. X is on its own. When I factor out a negative out of +4, that leaves us with -4. And then x plus 1 squared. So our leading coefficient now is negative. What are our roots? Well, we have 1 root at 4, right? There's no exponent, so there's just 1. And then we have -1, and it shows up twice because of that squared. So let's graph those roots. We have +4, -1. We're going to end up down here, so let's go ahead and graph that. At positive 4, we just pass straight through. And then at negative 1, we have a multiplicity of 2. So we kind of bounce back off, right? We have that parabola shape at that point. All right, y'all. This has been a pretty short lesson. Hopefully it's making sense. Thanks for watching.